In this session, we are going to try to visualize some vertical profile of the atmosphere. So you all know about these libraries because we just use them. Okay. Okay, let's open the data again. This is the same data set that we use throughout the whole tutorial. First of all, let's try to visualize the global circulation of the atmosphere, or general circulation. I think we usually call it general circulation, but not global circulation. Let me change it to general circulation. So first of all, I want to define the x-axis at latitude and the vertical axis as the height, or in this data set, the pressure levels. So I need to define them and assign them to a variable, and then use the mesh grid function to make the x-axis, the array of the x-axis and the y-axis. So I make the x-axis as the latitude and the y-axis as the pressure level. So I just do it here. And then, well, this is a very long code cell. Let's run it to see the result first, and then I will explain some of the features I have used here. And well, these are actually the code cells that I use to customize my plot. So these are not really necessary. It's just for the purpose to make your plot look more prettier. So let me introduce. So these are the basics, right? You need to assign the data array to here. I just take a mean of the longitude so that it only remains the latitude and the pressure level dimensions. And here I create a figure, yeah. And this function is used to make the y-axis become logarithm. This is the natural log. If you just type the log here, it represents natural log. So you can see from here, because pressure decreases exponentially with height, right? So I make the axis in natural logarithm, in the scale of natural logarithm. So to make it have a sense of height, yeah, to make it have a sense of height. So this is actually the scale of height is correct because the pressure is decreases from exponentially, and I said the x-axis have a scale like this. So it has a height scale. I mean, the length of the y-axis is in the height scale. Okay. So this is how I set the contour levels. You can see I actually set it between -55 to 55. And you can see from this contour level here. And these are the functions that I use to generate the contour lines and the labels. And this is the field contour, color contours. So basically, so these are the contour lines, right? So these come from these line of codes. So there are some colors here. These color contours come from these. And then there are some more customization that we need to make a vertical profile. First of all, the y-axis, we need to do a lot of things about the y-axis. And here we need to manually set the limit of y. Because by default, Matplotlib will generate your plot in ascending y-axis. But in pressure level, well, it decreases with height. It has the largest values at the bottom, and it has the lowest value at the top. So I need to manually reverse the order of the y-axis so that it can has the like 1000 at the bottom and then the 200 at the top of the plot. So this is yeah, the code to reverse the order of y-axis. And then here is, I set the y text. So this is the y text. I set the y text to make it happen every 100 hectopascal. So it happens like 1900 and etc. to 200. And then I also add some minor text. So here you can see the major text. It has a number on major text, but these are the minor text here. Because it's in log scale, the y-axis is in log scale. So I think, so it is better to add some minor text so that you can know which values between these two major axes belong. So it's like, okay, I now know it is like 280 hectopascal and like so on and so forth. And this is, okay, so this function, I may want to show it by example. So I make it a comment. I made this function a comment and I just draw the label again. You can see the label in y-axis. It becomes a scientific notation. And you need this function to make it a number instead of the scientific notation. It is a scalar formatter. It formats. It is a built-in function in Matplotlib to help you format your scalars numbers. So here. So I apply this scalar formatter within the set major formatter. So this is the function that Matplotlib uses to help you format the major text. So these are the major texts, right? So, and I apply this function to the y-axis of this axis object. Okay. So, and here, oh, these are the basics. So I set the x text and x text labels here. And then I set the labels here, and the title. So these are all about the whole code cell. Yeah, do you have any question about this one? And then for the next code cell, I leave it empty because I want you to plot the meridional wind structure. Well, basically, I have assigned this variable for you. And we can do this together because it's very easy. I don't know why I leave that empty actually. This is just by copying the whole code cell here. And then change the variable manually here. This is already a sonal wind component, right? I change it to meridional wind. Here, meridional wind. And change the title. And then this is the tricky thing. You need to change the contour levels because the scale of sonal wind and meridional wind are different. So maybe like I change it to maybe 5.5 here. Okay, I need to change the step also. So yeah, as a result, this is the meridional wind profile of the atmosphere. You can see here, this is the upward. The positive component of meridional wind is going northward. So you can see this is going northward and this is going southward. So this is like a general circulation. The sonal wind also, actually, you can see the jet stream right here, jet stream, and then the westerlies, and then the easterly in the tropics area. Here is the westerlies, right, jet stream. So this is the general circulation that I try to visualize from the data. And in these two code cells, I'm trying to plot also the vertical component of the wind factors. So which is called W. Because you have sonal as U and meridional as V, then vertical is just W, right? And But there is one thing to remind you in this data set, because in this data set, I've provided you this data. So this is the vertical velocity, but you can notice the unit is in Pascal per second. And actually you can approximate it to convert the unit from Pascal per second to meter per second by this equation. It just derives from hydrostatic, is it hydrostatic balance? It is from approximation, right? It is from approximation. So you can convert the unit from Pascal per second to meter per second by this equation. So this component is the W in the height coordinate. It's the vertical velocity in height coordinate. So it is a new unit of meter per second. But this component is called omega actually. This is the vertical velocity in pressure coordinates. So it has a unit of the Pascal per second. Also, I use ideal gas law to do this approximation, and then the formula is around this one. So this is basically to do the maths here, and I'll just remind you that the unit should be correct. And here I changed the hectopascal to Pascal by multiplying 100. And so this is the formula here. You can read it by yourself to understand it because it's just the formula here. Yeah. And okay, in this code out, let's run it to see the result first before we talk about it. You can see from here, the y component of the vector is the vertical velocity, and the x component of the vectors is the meridional component. So yeah, it's just like something like this here, but of course the magnitudes are wrong because here I first assigned a data array to a variable first, and then I have made some post-processing to the data so that because the scale of the vertical velocity is very small compared to meridional wing velocity. So if you don't do any pre-processing to the data and just plot it out, it will, because the meridional component is very large compared to the vertical, so it only has the vertical components in this plot. So I've done some pre-processing to the data to make it look more decent. For example, here, because the magnitudes of the V and W are different, so I vertically exaggerate the W components. How do I do this? I just make a scale here by defining the magnitude of meridional component and the magnitude of the vertical component. This is generally the magnitude scale between the V component and W component. And then I multiply the vertical component to this scale so that to make the two scales kind of comparable. And then I normalize all the wind factors to 1 so that it all has a magnitude of 1 because, well, if you scale the factor, the magnitude is not correct anyway. So I just normalize all the factors to 1. Then it makes this plot out. And these are, yeah, and the rest of the codes are all the same. And you create quiver plots to use this function to create quiver plots. And these are all the same functions that we used in the last cells. So this is all for this subsection.